Hello students, and welcome to the 5.03 teaching video for chemistry with Florida Virtual School. In this lesson we're going to be talking about gas laws. And first, before we actually get into the lesson material, I just want to quickly mention the objectives and the purpose of what we're trying to do here. In this lesson there's a few different things here that we're going to be able to accomplish. First off, we are going to be able to determine the meaning of symbols, key terms, and other domain-specific words and phrases as they are used in a specific scientific or technical context. Secondly, we're going to be able to look at graphs and understand the functions expressed symbolically, show key features of the graph, by hand in simple cases and using technology. We will also be able to make inferences and justify conclusions from sample survey experiments and observational studies. And finally, we're going to be able to interpret the behavior of ideal gases in terms of kinetic molecular theory. Now, the specific lesson objectives, we're going to understand the behavior of gases according to the kinetic molecular theory, and we're going to apply gas laws to predict outcomes. Now, the first thing that we have to talk about are the physical characteristic variables of gases. When we look at gases, there are different variables that we need to look at as we're talking about them. We need to look at the volume of the gas, we need to look at the pressure of the gas, what temperature it's at, and the number of particles. And we're going to look at the relationship between these four. Now, the volume, we typically measure that in liters when we're dealing with the gas laws. Pressure, we typically measure it in atmospheres. Temperature, we typically measure in Kelvin. And then the number of particles is always moles. Now, for these first three, I said typically because I'm sure you're all well aware that there are other units that are out there. For liters, we could also use milliliters, we could use cubic centimeters. So there's different units that can be used, but we like to put everything in liters. Same with pressure. We have pascals and millimeters of mercury. So there are other units of pressure, but again, we like atmospheres. Same with temperature. Of course, we have degrees Celsius, degrees Fahrenheit. For gas laws, we like to keep it in Kelvin. And one other important thing here is the ideal gas constant. We will use this throughout mainly 5.04, but we do want to make note of it here. It is 0.082 liter atmospheres per Kelvin mole is how you would say those units. And this is definitely a constant you want to have in your memory bank, so make sure you write that down somewhere and study on that one. Alright, so basically the relationships is what we're going to be looking at throughout this lesson. And really it's pretty simple. It's like any type of math problem. If you know three of the variables, you can easily solve for the fourth one. And we're going to look at these relationships as we go through. But before we look at the relationships, we need to talk a little bit about some of those different units specifically. First off, let's talk about pressure. Pressure is simply defined as the force per area on a surface. In other words, the pressure of a gas is due to the collisions of the moving gas particles with a surface, such as the wall, of the container, the balloon, whatever it happens to be that you're in. All right, remember, molecules and gases are constantly moving, and we'll talk more about that here in a second when we get to the kinetic molecular theory. But because they're moving, they, of course, are going to be bouncing into each other. They're also going to bounce into the wall of the container that they are in. Well, pressure is simply a measure of how much they hit the wall of the container. There are, again, some different units that we can use. The SI unit of pressure is the Pascal. Typically, we talk about kilopascals just because it is a very small unit. Now here is just the relationship between some of these different units of pressures. 1 atmosphere. All right, basically what that is if you're standing at sea level, the atmosphere above you, however much pressure that is pushing down on us, that is what we call 1 atmosphere of pressure. Well, that is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 101.3 kilopascals. And in America, of course, we use PSI, pounds per square inch. So just a little side note here, if I may add this in, it is 14.7 pounds per square inch. Okay, so all of those are equal to each other. And again, this is the amount of pressure that we have at sea level. And this is also what we call standard pressure. All right, so all of these values here are what we call standard pressure. And that is something that we're going to need to use when we get to lesson 5.4. All right, so just kind of keep that in mind also as we're moving forward. Now, because we do have different units of pressure, sometimes we're going to have to convert between them. You may be given a problem that says, hey, you have 852 millimeters of mercury, but remember we said a couple slides ago that we always wanted it in atmospheres. So we need to convert this really quick to get it in the units we want. So the first thing that we should do is figure out which conversion factors we actually need. Well, if we go back one slide, we're starting with millimeters of mercury, and we need to finish with atmospheres. So we're going to use this top equality. 1 atmosphere equals 760 millimeters of mercury, and we're going to use that as our conversion factor. And then the second part is, of course, just to go ahead and complete the conversion. So let's write this down here. We have 852 millimeters of mercury. And again, we need that in atmospheres. So we set up our conversions just like we did back in segment 1. Set it up as a fraction. That way we can make sure we're canceling out our units properly. Now, since we have millimeters of mercury on top at the beginning here, that means we need to have it on the bottom in the conversion factor so that we're canceling out the units. So we put our 760 on the bottom, and then we put the 1 atmosphere on top. And again, that allows us to cancel out millimeters of mercury since we're dividing them. And when we do the math there, it's going to be 852 times 1 divided by 760, and we get 1.12 atmospheres. Okay, so that's how we do our pressure conversions. We just simply look at that chart on the previous slide, determine which conversion you're going to use to get it from whatever you're given to what you need, which again typically it's going to be atmospheres. Now we also have to convert temperature. All right, remember we mentioned we want to have it in Kelvin. A lot of times you're going to be given Celsius. Well, to convert between those two, real simple formula. Kelvin simply equals the degrees Celsius plus 273.15. Now, a lot of times we just drop off the 0.15 and just use 273. That is acceptable in most cases. All right, so if you see a practice problem that is doing it that way, that's perfectly fine. And if we're going the other direction, well, we just reverse that. Degrees Celsius equals Kelvin minus 273.15. So for our example here, if we have 35 degrees Celsius and we need that in Kelvin, we are again just going to add that 273.15 to it. So we have 35 degrees Celsius plus 273.15, and that's going to give us 308.15 Kelvin. Now please note that there is no degree sign on Kelvin. That's because it is a theoretical scale based on absolute zero. So you don't put the degree sign in there, only the K when you're dealing with a Kelvin scale. Okay, so now we're going to look at the nature of gases. A lot of this we already talked about in 5.2, but we do need to touch on it some more here. At normal, as we call them, temperature and pressure conditions, gases are going to behave ideally. Basically, normal means that we're kind of in the mid-range. We're not extremely high with temperature or pressure, and we're not extremely low with the temperature and pressure. So basically like room conditions, room temperature, room pressure, those are typically in the ranges that we work with. In those situations, there's some properties of gases that we can talk about. One is low density. All right, the gas molecules again are spread out, and they're flying around in the space there. And whatever the space is you're measuring, because they are so spread out, there's very few of them within it, so it's going to have a low density. Because again, density is how much matter is in a given volume. Compressibility. Of course, we know that gases, because they are spread out like that, there's lots of empty space between them. Therefore, we can push those molecules closer together. And that is called compressibility. Expansion. Just the opposite of that. If you take a certain amount of gas particles and you put them into a bigger container, then they are just going to naturally spread out and fill that container. So just as you can compress them, they can also easily expand. Diffusion. A great example of diffusion is if you ever had somebody maybe spray some perfume or something in the room, and they're on the other side of the room. Initially, you don't smell it. After 30 seconds or so, now you can smell the perfume. That's because that gas is diffusing. And basically what that means is it's going from an area of high concentration and it's spreading itself out to other areas that have lower concentration until it's evenly mixed. And then finally, fluidity. In other words, it flows. Gas molecules, because they're able to move around and glide, if you will, past each other, they can flow. Much like water, for an example, liquids, flow. Gases also flow. They're able to move. Now, all of those properties can be explained using the kinetic molecular theory. All right? An ideal gas is an imaginary gas that behaves according to all assumptions of the kinetic molecular theory. Now again, we have to talk about them in ideal situations because, of course, we live in a real world with real gases, so they do not always follow exactly the things we're going to talk about here, especially when, again, they're at those extreme conditions of temperature and pressure. So there are some assumptions in the kinetic molecular theory that we have to follow. First off is that gas particles are in constant random motion. All right, and they're always moving. They don't stop. Secondly, they occupy a volume of 1,000 times greater than that of a solid or liquid. In other words, there's lots of empty space between them. Okay? Lots of empty space. Thirdly, gases have elastic collisions. In other words, when two gas particles collide with each other, they bounce off of each other. There is no loss or gain of the total kinetic energy between them. In other words, if molecule A has 10 joules of energy, molecule B has 20 joules of energy, so total they have 30 joules of energy between them. When they collide, they're going to bounce off of each other. Now they may transfer some energy. After the collision, maybe they both have 15 joules of energy, but the total is still going to be 30. There's no net gain or loss of the kinetic energy. Fourth assumption is that gas particles move so quickly that the attractive forces between them are negligible. And so in other words, we can ignore them. Because the gas particles are spread out and they're moving very quickly, we can assume that there's no attractive forces between them. And then lastly, the higher the temperature, which we measure in Kelvin, the greater the average kinetic energy of a sample. And you remember in earlier lessons that we talk about how temperature is a measure of average kinetic energy. So obviously if it's a higher temperature, we're going to have a higher average kinetic energy within the gas particles. All right, so that concludes part 1 of the 503 lesson. All right, so now let's look at part 2. In part 2 of this lesson, we're actually going to look at the gas laws themselves. The first one we're going to look at is the relationship between pressure and volume. This is an inverse relationship. And what that simply means is as one volume increases, the other decreases. One goes up, the other goes down. This is called Boyle's law. And Boyle's law simply says there's an inverse relationship between volume and pressure when temperature and number of moles are held constant. Remember in part 1 we talked about there's those 4 variables: pressure, volume, temperature, number of moles. In this example, we take temperature and moles and we hold them constant. So the temperature is the same throughout the entire experiment. The number of moles is the same throughout the entire experiment. And then we see what happens to the pressure and volume. Well, it is an inverse relationship. So if the pressure goes up, the volume goes down. And a perfect example of that, if you take a container and you apply pressure to that container, it is going to shrink. If it's a hard container, you're crushing it at that point because you have a greater pressure, so you're going to end up with a smaller volume. And the mathematical relationship then would look like this: P1 V1 equals P2 V2. The P's, of course, stand for pressure. V stands for volume. The 1 and the 2 simply tells us the first set of data versus the second set of data. So let me show you an example of a type of question that you would have. All right, a 2-liter container of nitrogen has a pressure of 3.2 atmospheres. What volume would be necessary to decrease the pressure to 1 atmosphere? All right, so we're going to use that formula that we just had on the last page. Okay, we got P1 V1 equals P2 V2. All right, now when we look up here, we have 2 liters and it has a pressure of 3.2 atmospheres. So that would be our first set of data, right? So the P1 is 3.2 atmospheres. That is our pressure. The V1 is a 2.0 liters, the volume. Okay, then they give us a new pressure, so that must be P2. And we're solving for V2. And we're solving for the new volume. What volume would be necessary? So that's what we're solving for. So now we just come down here and plug in our numbers. 3.2 atmospheres times 2.0 liters equals 1.0 atmospheres times V2. Okay, so we got 6.4 atmosphere liter on this side equals still 1 atmosphere times V2. And then of course to get the V2 by itself, we have to divide both sides by the 1, right? So we divide that side by the 1, we divide that side by the 1, so they'll cancel out. And of course anything divided by 1 is going to stay the same. So our final answer is 6.4 liters equals V2. All right, so again, we're given 3 of the 4 variables. It's just a matter of first making sure everything is in the correct units. Here we have atmospheres, so we have to have atmospheres on the other side. Liters, so we're going to have liters for our units on our answer. And then secondly, just making sure you've got the variables paired up correctly based on the information you're given. Plug it in and then solve for the missing one. All right, the second relationship is a direct relationship, and this one is going to be between temperature and pressure. Direct relationship means that if one goes up, so does the other. All right, they both go the same direction. This one is called the Gay-Lussac law, and that law simply says there's a direct relationship between pressure and temperature when volume and number of moles are held constant. So again, we got our four variables. This time it's going to be volume and number of moles that are held constant. So the container that we're working with is going to stay the same size. The number of particles in the container are staying the same. And we're going to look at the relationship between pressure and temperature. And it is direct. So if we increase the pressure in the system, the temperature also has to go up, and vice versa. So down here on the bottom is the mathematical version of that. P1 divided by T1, since it's a direct relationship, equals P2 divided by T2. Again, first set of data and the second set of data. P again is pressure, T is temperature. So let's look at an example problem for this one. Chlorine gas has a pressure of 1.5 atmospheres at 300 Kelvin. What would be the pressure at 600 Kelvin? All right, so again, we need to pull out the information we are given. We're told that our first pressure is 1.5 atmospheres. Our first temperature is 300 Kelvin. We want to know the new pressure when the new temperature is 600 Kelvin. All right, so again, we got our formula. Take me just a second here to write it up. P1 divided by T1 equals P2 divided by T2. Okay, so it's just a matter of plugging those in. All right, so our P1 was 1.5 atmospheres. T1 was 300 Kelvin. P2 is the one we're solving for, and T2 is 600 Kelvin. All right, so now when they're equalities like this, of course, you know in math we cross multiply. So 1.5 times 600, P2 times 300. I got 600 times 1.5. That's equal to 300 times P2. All right, so on the left side we have 900 Kelvin atmosphere equals 300 Kelvin P2 on the right side. And we're going to divide both sides by the 300. And that will get us our final answer, which is, of course, going to be 3 atmospheres for P2. Right, so again, same type of situation, just pulling out the information we're given and plug it into the formula in the correct locations and then solve for the missing variable. The third relationship is going to be between temperature and volume. Just a moment ago we did pressure and volume. Now we're going to look at temperature and volume. This is also a direct relationship. So if we increase the temperature on the system, the volume increases. If you take a balloon, for an example, it has a set number of moles and has a set pressure in there because of the number of moles. Well, if we put it, say in a freezer, for an example, we're lowering the temperature, the balloon shrinks down. If we, put it outside in the sun, it warms up, so it expands. Right? That's the direct relationship between volume and temperature. This is called Charles's law. Direct relationship between volume and temperature when pressure and number of moles are held constant. So again, we hold two variables constant. We look at the relationship between the other two. And since it is a direct relationship, they would be divided. So V1 divided by T1 equals V2 divided by T2. Alright, so let's go ahead and look at an example of that one. Hydrogen gas was cooled from 150 degrees C to 50 degrees C. Its new volume is 75 milliliters. What was its original volume? All right, so again, we got to pull out the information we're given. We know that the initial temperature, T1, was 150. Then they asked, or said that the new temperature is 50 degrees, and the new volume is 75 milliliters. And we're being asked then to solve for the original volume. So we're solving for V1 this time. All right, well again, our formula, V1 divided by T1 equals V2 divided by T2. All right, so V1, that's the one we're solving for. T1 was 150 degrees Celsius. V2 was 75 milliliters. And the new temperature is 50. Now, just a little note here. This is in milliliters. And I'm leaving it in milliliters simply because I can now leave the units for my answer in milliliters. If you want to change that to liters first and then solve this out, that is perfectly acceptable. That'll work fine. That is probably a good practice to do, simply because when we get to 5.04 and we start doing the ideal gas law, we do always have to be in liters. So it's probably not a bad idea to go ahead and get in that habit now. So let's go ahead and do that. To get from milliliters to liters, remember we simply divide by 1,000. Right, 1,000 milliliters in a liter. So if we, come on now, we take our 75 there, divide it by 1,000, and we're going to have 0.075 liters. Now, we'll get you the same answer in this case, but again, when we do get to the ideal gas law, it always has to be in liters. So, all right, so we cross multiply. So we're going to have 50 degrees C times V1 equals 0.0075 liters times 150 degrees C. Oop, my decimal did not show up in there. There we go. Alright, so on the left, again, it's still 50 degrees C times V1, and that is equal to 11.25 liter degrees Celsius. Alright, so again, we gotta now divide both sides by the 50. To get our final answer, and V1 will equal 0.225 liters. If we multiply that by 1,000, that would be 225 milliliters. Alright, so that's how we do Charles's law. Alright, and then the last law that we have in this lesson is Avogadro's. In this one, again, we have a direct relationship between moles and volume. So in this case, it's pressure and temperature that we're holding constant. And as we increase the number of moles, we're also going to increase the volume. So in other words, if we have a container that has and we want to keep the pressure and temperature the same, if we start putting more gas particles into it, then it's going to have to naturally expand. Again, using the balloon example, if you haven't closed it off yet and you're blowing into it, you're putting more gas particles into it, so the volume is getting bigger. So the mathematical relationship, because it's direct, we're dividing, so it's V1 divided by N1 equals V2 divided by N2. And again, N represents the number of moles. So an example for this one, 2.4 moles sample of nitrogen occupies a volume of 250 milliliters. What volume will 4.1 moles occupy? Alright, so again, just pulling out our information here. We got N1. We started with 2.4 moles. It had a volume of 250 milliliters. Again, if we divide that by 1,000 right now, that's going to give us 0.250 liters. Alright, and what volume will 4.1 moles occupy? So now we have 4.1 moles, and we need to solve for V2. Alright, so again, the formula was V1 divided by N1 equals V2 divided by N2. So we just need to plug in what we have. Alright, so the first volume was 0.250 liters. The number of moles was 2.4. Alright, on the right side, the new moles are 4.1. And we need to figure out V2. So cross multiplying, we get 0.250 liters times 4.1 moles. That's equal to 2.4 moles times V2. So now on the left side, we've got 1.025 liter mole. And we still have 2.4 moles V2 on the right side. Again, to get V2 by itself, we gotta divide both sides by the 2.4. And that gets us our final answer, where V2 is going to be 0.427 liters. And again, if we multiply it by 1,000, it would be 427 milliliters. Either one would be an acceptable answer. All right, now the last one we're not actually going to look at any math for, but we do just want to mention the relationship here. And that's between pressure and moles. All right, in this one, if we have volume and temperature constant, the more particles that are present, the greater the number of collisions we would have. So we're also going to have a higher pressure. So it is a direct relationship. So if we increase the number of particles, we also increase the pressure. All right, moles goes up, pressure goes up if volume and temperature are held constant. And again, we don't have any mathematical formula for that one. We could certainly make one, be just like the other three that we've looked at prior, but we don't usually deal with those type of situations in the lab, so we don't really use that one. All right, so that concludes our 5.03 lesson. Hope this was helpful for you. There's other recordings and practice problems that you can definitely check out. And always, if you still need some more help, feel free to join us in the tutoring room. We'll see you there.